Welcome to the Depth Dive, the show where we really try to cut through the noise, get straight to the core ideas from the latest research. We want to give you those critical insights without you having to wade through all the dense equations. Today, we're ripping apart a performance study. Honestly, it's essential reading if you're involved in designing or provisioning infrastructure for these, massive next-gen language models. The paper's called Efficient LLM Inference. Bandwidth, compute, synchronization, and capacity are all you need. And it's crucial because it lays out these fundamental hardware truths, the non-negotiables that dictate how fast we can actually run auto-regressive decoding on models like Llama 3.
That's exactly right. And our mission today really is to walk you through the findings from their model, which they call Liminal. That's LLM Inference, memory bandwidth, and latency. And the beauty of Liminal is that it's hardware agnostic. It lets us see the universal performance limits. Doesn't matter if it's today's HBM3 stuff or, hypothetical future systems, maybe with 3D stacked DRAM. It's all about these huge models like Llama 3 405B, DeepSeek V3.
Okay, perfect. So for anyone needing the quick version right now, maybe you're grabbing coffee, this is your 1-minute summary. The key insights, ready for that short form edit?
All right, here we go. 5 non-negotiable truths for efficient LLM serving, straight from this fundamental analysis. First, capacity. It's step 1, not an afterthought. You need hundreds of gigs of memory per system for these big models at long context. We're talking up to 1.4 terabytes for something like Llama 405B in certain scenarios. Can't fit the KD cache and weights. You're basically dead in the water. Second, bandwidth. Memory bandwidth is the absolute core constraint. LLM serving is just starved for it. Current HBM3 systems, they hit a wall, a hard plateau around 750 user throughput per second, or UTPS for the biggest models. Third, synchronization. This one's the hidden killer. Got tons of bandwidth, great. But it's useless if your collective communication is slow. Those exposed sync latencies between chips, they have to be down around 1 microsecond. Otherwise, all that fast memory just sits idle. Fourth, DRAM efficiency. Here's where DRAM shines. Because it gives you capacity and flexibility, DRAM-based designs win out fundamentally on system-level efficiency. So think throughput per dollar or throughput per watt. Way better than, say, pure SRAM designs that lack the capacity.
And finally, number 5, algorithms. The only way we get to the next level, like 10,000 UTPS, is through Algorithmic Co-evolution. Hardware alone, even future stuff, seems to top out around 2,800 UTPS based on these projections. We need new algorithms for more parallelism, or maybe smaller models, smaller contexts.
Wow, okay. 5 points. Sounds simple laid out like that, but yeah, built on some serious systems modeling. Let's dig in. So let's unpack this. The core problem they're looking at is autoregressive decoding, right? That's the bottleneck, especially when you have these really long context windows. It just dominates the latency.
Exactly. And the liminal framework is really powerful because it simplifies things. It abstracts away the nitty-gritty details. It looks at 2 main things. The application, the LLM itself, defined by how much data it needs, how much compute, and its synchronization demands. And then the hardware, the XPU, whatever accelerator you're using, defined by its compute speed, its memory bandwidth, its capacity, and importantly, the delay talking between chips.
Got it. So you're modeling the sort of fundamental physics of the system, the constraints, not simulating a specific NVIDIA GPU or Google TPU down to last transistor.
Precisely. And that lets us boil it down to this key equation for the mini-batch latency, 2-batch. Basically, the latency is the longer of either the time spent computing or the time spent moving memory, plus this extra bit, the exposed latency, de-exposed RAMs, and that memory time. It's almost entirely fetching the model weights and dealing with that KV cache, which just grows and grows.
Okay, and that third piece, T-exposed, what exactly is that again?
Right, T-exposed, that's the crucial one, really. Think of it as unavoidable waiting time. You're running distributed, right, across multiple chips. T-exposed is the time your chip is just sitting there, idle, waiting for the other chips to finish their piece of the puzzle, to synchronize before the next step can happen. That's your synchronization latency. Specifically, TP sync when you're doing tensor parallelism.
And how does this change when you scale up? The paper talks about 2 main ways to spread the work, right? Strong scaling and weak scaling.
Correct. 2 fundamental strategies. Strong scaling is mostly about tensor parallelism, or TP. You chop up the model operators, spread them across lots of chips. The goal is lower latency for a single user's request. They assume 3 sync operations, like collectives, per layer for TP in their model. Then there's weak scaling, which is usually pipeline parallelism, or PP. This boosts the overall system throughput, more users served over time, but doesn't necessarily make things faster for any one specific user.
Okay, so TP for faster response, PP for more total users. Got it. Let's pivot to memory then, because key finding 1, capacity, you said it's the prerequisite, and this is where the numbers just get, kind of insane. Let's use that Llama 3 405B example. Big model, big context.
Yeah, the KV cache numbers are staggering. I mean,
Period.
really, take Llama 3 405B, a single user, just one, at a 64,000 token context length. That needs 15.75 gigabytes just for their KV cache.
15 gigs for one user.
For one user. Now imagine you want to serve a batch of, say, 32 users at the same time to be efficient. That's over 500 gigabytes just for the cache data. Add in the model weights themselves, and that system needs 881 gigabytes of memory total just to handle that one scenario.
Wait a sec. 881 gigabytes for one, fairly common long context scenario. Is that basically saying that, like, standard cloud GPUs today, even if you cluster a bunch of them, they can't handle these models at long context unless they completely rethink their memory?
That's exactly the implication. Capacity isn't just about fitting the model anymore. It's fundamental to maximizing your system throughput, your STPS. You need that huge capacity to allow for larger batch sizes. Bigger batches mean more reuse, better efficiency overall. Which brings up an important distinction. UTPS user throughput per second. That's about low latency for the individual. Then there's STPS system throughput per second. That's total tokens served, which ties directly to cost efficiency.
Okay, capacity is the foundation. Then the second pillar you mentioned, bandwidth. You talked about arithmetic intensity, AMI.
Right, AMI. The paper quotes it around 41.56 FLOPs per byte for Llama 3 405B at batch 32.
Okay, maybe give us the quick, conceptual definition. What is AMI, and why does that number, 41.56, tell us something important?
Sure. Arithmetic intensity, AMI, is basically a ratio. It's how much math, how many floating point operations, or FLOPs, you get to do for every single byte of data you have to pull out of memory. If AMI is high, it means you do tons of calculation for each byte fetched. You'd be compute bound. The fact that it's low here, only 41.56, confirms what we sort of intuitively knew. LLM serving, especially decoding, is overwhelmingly memory bandwidth constrained, not compute bound. It's like the highway is jammed because you're constantly moving data back and forth, not because the car's compute units aren't fast enough.
Right, okay. The data highway is jammed. So what are the current speed limits on that highway? What did the study find for today's tech?
Well, with current state-of-the-art HBM3 systems, even if you link up, say, 128 chips using tensor parallelism, you still max out around 776 UTPS for that big Llama 3 405B model. And key finding 3 here is pretty stark. No HBM3 base hardware, as it stands, can break the 1000 UTPS barrier for these large models at long context lengths.
776 UTPS. That sounds like a lot, but I guess if you're a major cloud provider trying to serve millions, that's a hard ceiling.
It's a definite bottleneck for scaling the biggest, most capable models widely.
But okay, future memory tech looks better, right? HBM4, maybe 3D stacked DRAM.
Yes, definitely potential there. The analysis shows that doubling or even quadrupling the memory bandwidth gives you a significant boost. We're talking up to maybe 3 times the UTPS. That could push performance for these large models into the, say, 1500 to 2800 UTPS range, even at 128K context. So initially adding more bandwidth, huge wins.
Okay, but the data also shows that just keeps pouring more bandwidth on doesn't work forever. You eventually hit another wall. Why is that? If bandwidth was the bottleneck, what happens when we have enough?
That's where our friend Teaxpo's the Synchronization Gatekeeper comes crashing in. Key finding 5, right? Once you move to these really high bandwidth systems, think hypothetical 3D DRAM, or maybe even SRAM-based systems, which could be like 8x to 30x faster than HBM3, that synchronization delay, TTP sync, it suddenly becomes the #1 factor determining performance. You might be able to fetch data almost instantly, but if your chip then has to wait, say, 10 microseconds for the other 127 chips in the group to acknowledge and sync up, well, you've just completely wasted all that expensive fast bandwidth.
Okay, so the coordination becomes the bottleneck. What kind of speed do we need for that coordination, those collective operations, to actually make use of the faster memory?
The analysis is pretty clear. You need sub-microsecond all-reduced latency, ideally right around the 1 microsecond mark, maybe even slightly less, and that's across potentially 64 or 128 chips working together. If you can't sync up that fast, the super high-speed memory just doesn't deliver the promised performance gains. It's ineffective.
Huh. And there was that really interesting kind of counterintuitive finding you mentioned earlier about balancing sync speed and the number of chips.
Yes, this was fascinating. On current HBM3 systems where the bandwidth is, let's say, modest, right? Not terrible, but not blazing fast, the study found something unexpected. Running with high tensor parallelism, like spreading the work across 128 chips, TP128, even if the communication latency between them is relatively large, that can actually give you better performance overall than using fewer chips, say TP8, even if those 8 chips could sync up super fast.
Wait, so slower sync across more chips beats faster sync across fewer chips, but only when bandwidth is limited.
Exactly, when bandwidth is the main constraint. Think of it this way. If your main internet pipe bandwidth isn't huge, it's actually better to open up 128 smaller parallel downloads, TP128, to maximize the use of that pipe, even if coordinating all 128 takes a bit longer, higher sync latency per operation, than trying to force 8 massive downloads, TP8, through that same limited pipe, even if those 8 could start instantly, low sync latency. It really highlights that you need a balanced approach. You often need to distribute the load widely just to aggregate enough bandwidth from all the chips, even if it slightly increases the communication overhead for each step.
Okay, that makes sense. Balance is key. So we need massive capacity, massive bandwidth, and super fast synchronization. But all of that costs money, it costs power. How does this translate into practical advice for, the system architects actually designing these data centers?
It really boils down to efficiency, right? Throughput per watt or per dollar. Precisely. And this brings us back to key finding 4. When you look at efficiency metrics, SDPS per watt or SDPS per dollar, DRAM-based systems like HBM3 or future HBM4 show a fundamental advantage. Why? Because compared to alternatives that might offer super high UTPS but are very limited in capacity, like maybe an all-SRAM design, DRAM gives you that crucial capacity and flexibility.
Yeah.
You can support larger batches, which drives up reuse and therefore system-level efficiency.
Right. And how does efficiency play out differently for different types of models? You mentioned dense ones like Llama versus sparse mixture of experts like DeepSeek v3.
Yeah. Efficiency always comes down to maximizing reuse. For dense models like Llama 370B, especially at smaller context lengths, you get incredible weight reuse. The same model weights get used over and over. This can lead to huge efficiency gains. The paper mentions sometimes almost a 30x improvement in STP SWAT if you're willing to accept a very small hit to the user latency, the UTPS. For sparse MOE models like DeepSeek v3, the game is expert utilization. If you run a tiny batch size, maybe just one user, only a couple of the experts inside the model activate, it's inefficient. But if you crank up the batch size to, say, 32, suddenly you're engaging many more, maybe all of the experts much more effectively. Again, you might trade a tiny bit of responsiveness for a massive boost in overall system throughput per watt.
But crucially, you also mentioned those efficiency gains aren't like a free lunch forever. They diminish.
Correct. That's key finding 7. While these reuse tricks offer amazing efficiency benefits, especially weight reuse and expert utilization, those benefits get dramatically challenged as the context lengths grow really, really large. As that context window expands out to hundreds of thousands of tokens, the efficiency gains from simple batching start to diminish quite rapidly.
Okay, so let's look ahead then. The analysis shows near future hardware, HBM4, 3D DRAM, that might get us towards, 2800 UTPS? But if the industry is dreaming of, say, 10,000 UTPS, where does that come from? Is it just even more bandwidth and faster sync?
Well, according to this analysis, probably not. The hardware itself seems to hit diminishing returns past that roughly 2800 UTPS ceiling. You've maxed out the memory bandwidth you can reasonably provide, and you're hitting those fundamental synchronization limits. So the path to 10,000 plus UTPS, it seems, must involve algorithmic co-evolution. We need fundamentally new algorithms, maybe things that introduce more parallelism within the autoregressive step itself, or perhaps approaches that dramatically reduce the effective model size or the context size requirements without hurting quality. The solution likely isn't just throwing more silicon at the current methods.
And given that we'll likely have all sorts of different models coexisting, some big, some small, some dense, some sparse, which hardware strategy seems best positioned to handle that kind of future, that algorithmic evolution? Flexibility seems key.
Absolutely. And that brings us back to key finding 9, which really favors the flexibility of DRAM. DRAM provides that blend of density, capacity, and bandwidth. And crucially, DRAM-based systems can be organized into these very large chip groups, like the TP128 configurations we discussed, which seem necessary to handle the diverse mix of models, context lengths, and user experience trade-offs we're going to see. It seems the most adaptable approach.
Okay, one last quick point. Compute. It's one of the 4 pillars in the paper's title. Capacity, bandwidth, synchronization, and compute. Is compute ever the bottleneck?
In short, rarely for LLM and decode. It's just so heavily dominated by moving data bandwidth and capacity constrained that the actual compute units, the ALUs, are often sitting idle. The paper shows compute utilization can be less than 1% in low batch scenarios on typical DRAM or even SRAM accelerator designs. The main exception they found was for specific cases, like maybe the DeepSeek v3 MOE model running at a large batch size but with a small context length. Then you might become compute bound. But even that tends to ease off as the context length grows and memory becomes dominant again.
Okay, so we've covered the 4 pillars: capacity first, then bandwidth, then the crucial synchronization speed, and finally compute, which is usually not the problem. The big takeaway seems to be that LLM inference performance isn't about tweaking one single knob. It's this really delicate, tightly coupled balance between all 4.
That is absolutely the critical insight for everyone listening, especially if you're an ML engineer or a researcher building or using these systems. When you're provisioning infrastructure, you absolutely have to avoid optimizing for just one thing in isolation. If you go out and buy the absolute fastest memory bandwidth available, but you don't provision enough capacity to fill it, or you neglect the interconnect and end up with slow synchronization, you're just wasting money and power. You need that balanced approach across C, B, and S capacity, bandwidth, synchronization, and making sure you actually have enough compute for the rare cases it matters.
Yeah.
It all has to work together.
Right. And that leads perfectly into maybe a final provocative thought for our listeners, building on that efficiency discussion. We talked about how those huge power efficiency gains, those potential 30x improvements in STPS watt, they're really tied to maximizing reuse, weight reuse, expert reuse, which works best at smaller context lengths. But if those efficiency gains really drop off as context gets super long, it poses a really interesting question for future research, doesn't it? What kind of unexplored algorithmic tricks are out there? How can we maximize weight and activation reuse even when dealing with these extremely long, hundreds of thousands of tokens context windows without completely tanking the latency that the user experiences?
Yeah, finding ways to maintain high reuse and efficiency as context scales into the stratosphere, that feels like the next big algorithmic frontier. That's where the breakthroughs might need to happen.
Absolutely. Well, thank you for joining us on this deep dive into the fundamental performance limits of LLM inference. We really hope this distillation helps guide your thinking, maybe your next hardware design decision or system deployment.